recording too. All right, so just to recap, assume we have a capacitor, a parallel plate capacitor. So the plates have area A and they're separated by a height. Let's make it D. Well, in fact, let's make this area A1 and area A2 like that. And then we've deposited charge plus Q on the top plate and a minus Q on the bottom plate. How are we going to figure out the capacitance of this structure? So with this capacitor problem, we have a total charge on here. We also know some things about perfect conductors, right? So if these are perfect conducting plates, we know that there can't be any sideways electric field. The electric field has to be normal to it only, right? Because of our boundary condition that we just derived, E2 minus E1 n cross that is 0. But since there's no electric field inside a perfect conductor, that just means that the tangential component of the electric field touching this conductor has to be 0. So we have, let's set it up this way. We know some facts. The facts that we know are V1 equals V2. I'm going to write down, my first step is going to be write down all the facts. And we also know that at this boundary, the boundary between these two dielectric materials, the parallel components of the electric field have to be equal, which also supports V1 equals V2 because they're both connected by this PEC thing on either side. So they have to be the same horizontally. And also here at this interface, the two electric fields have to be equal, right? So E1 equals E2. I said that there's a total charge deposited on these plates. But if these two electric fields are equal, and we know Gauss's law, if the electric fields are equal and they have different dielectric constants, what is true about the electric flux densities? Does D1 equal D2?
Because the field is, the field is dependent, the flux density is dependent upon the E times the field. And if E is changing, then that means the field, well, the other component has to be changing.
Right. So
I'm getting my terms mixed up.
Yeah, but like flux density 1 does not equal flux density 2 because epsilon 1 E1 does not equal epsilon 2 E2, even though E1 equals E2. Is that what you're saying?
Yes.
Yeah. So that's good. Cool. But that means, what's going on with the charge here? If we think about what our Gaussian surface might look like, if we draw a separate Gaussian surface for like this area and this area, and say that we have Q1 over here and Q2 over here, let's say that these areas are equal in size, right? Q1 and Q2 are not equal because D1 and D2 are not equal. Or we could write this as the surface charge 1 does not equal surface charge 2, which is true no matter what the areas are. Make sense so far? So to solve this problem, what we actually need to do is assume a voltage. So my second step, now that I know all these facts, is going to be to assume a voltage and to make some symmetry arguments about the direction and behavior of the electric field. So I'm using the symmetry of the problem, the geometry of the problem, and the boundary conditions to say what direction the electric field is going to point, and the fact that it's going to be uniform all the way through, right? We said that it's perpendicular to the plates because they're perfect electric conductors. We said that it is equal across this interface. We said that the voltage is the same all the way across, and because we know that the electric field is, we know that the voltage is minus the integral of the electric field dl, that means that the electric field must be the same everywhere because the voltage is the same everywhere. Everybody with me so far? So if we assume the voltage, then we can find the electric field. And then after that, we can find the electric flux density. And then after that, we can find Q. And then we have Q and we have V. So then we can find that the capacitance is Q over V. Those are the steps that I want you to go through as you try this in your breakout rooms.